Okay, we'll go ahead and get started. I want to welcome everyone to the second day of the APO Science Symposium. My name is Denise Stevens and I'm at BYU, so we're part of the newest group to join, Apache Point Observatory, so we're super excited to be involved. And Nancy asked me to moderate this first session, this Tuesday morning session on minor bodies and moons. I just want to remind everyone that there are 3 different ways you can ask questions. So you can post them in the Zoom chat, you can post them on the Slack channel, or just raise your hand. It'd probably be easiest for me at the end of the talk. And then of course, we do have a meeting code of conduct posted on the meeting homepage. And so make sure you've read that and understand. We have a lot of students presenting. We want things to be professional, concise, and really respectful. So it's a great opportunity for the students to present. And so we're excited to hear from them. And then for each speaker, you'll have 12 minutes for the talk and 3 minutes for Q&A. And I have figured out how to put the video background up in myself that has the little countdown timer. So you want to pin that to your page. You'll see the colors change. And then if you get into the red, I'll start to say something. But our first talk today is going to be Adam McKay. He's from the American University NASA Goddard Space Flight Center. And his talk is on exploring the volatile composition of comets with ARSIS. So I will turn the time over to Adam.
All right, thank you very much. So I'm going to provide a brief overview of our campaign of observing comets with ARSIS over the last decade or so, dating back to my time as a graduate student at New Mexico State University. I'd like to start by first acknowledging my collaborators, which are all listed here. But I particularly want to acknowledge Neil, who is at the Johns Hopkins Applied Physics Laboratory, and he serves as the PI for our current proposals through APOS, as I am not currently at an ARC institution. So thanks to Neil for that. Okay, so the little background on kind of why we care about cometary composition. So comets are primitive leftovers from the formation of the solar system. And because of this, they are not very altered, and that we believe that their physics, their composition reflects the physics and chemistry occurring in the protosolar disk during planet formation. So hopefully by studying the composition of comets, we can get a better understanding of planet formation processes. So specifically, as I kind of mentioned, we've been engaged in a very long spectroscopic campaign to study comets spectroscopically at optical wavelengths using primarily 2 facilities. So one is the Tull-Coudet spectrograph at McDonald Observatory, but the other, which obviously is more the focus of this talk, which is using ARSIS at Apache Point. So when we look at the optical spectrum of a comet, they are dominantly emission line objects. There is also some continuum due to solar radiation reflected off of dust particles in the coma, but the dominant features are these strong emission features. These are kind of some atomic species like atomic oxygen, but also simple molecules like diatomic carbon and CN as well. So this is an ARSIS spectrum that we took of a comet called C2012 S1 ISON back in 2013. And so when you look at it at this large scale to try to cover all the emission features, you really lose the detail that we get and the benefit of using an instrument like ARSIS. So when we actually zoom in on some of these specific emission features, you can see the tremendous detail that we can get in these spectrum, these spectra of comets. So when we look at the high spectral resolution that ARSIS provides, all of a sudden now we can see this detailed molecular band structure, like here for CN and also here for C2 as notable examples. You can also see isotopologues of these different molecules, as well as reveal a molecule or species that have telluric counterparts like forbidden oxygen, which I'll talk about in a few slides. All right, so kind of scientifically, what do we actually do with these spectra? So one thing that we've been able to do a lot with APO is actually look at the temporal variability of comets. So comets are very dynamic objects. They change their activity level and observe coma composition over their entire apparitions. So it is very important to not just observe them once, but observe them at multiple times over long time periods. So for instance, you can look at the overall activity level here. So when we looked at the water production of C2012 S1 ISON, we followed it with APO all the way from when it was 1.8 AU away from the sun, all the way in to about half an AU from the sun. And we're able to monitor its activity level over that time period. But also we can look at how the composition of the coma actually changes as well. So here's an example from my PhD work of a comet called C2009 P1 Grad, where we looked at the C2 to CN ratio when we followed it in from near 3 AU from the sun all the way in near to its perihelion passage, which was about 1.6 AU from the sun. And we saw that there was this dramatic increase in the C2 to CN ratio as the comet moved towards the sun. This is probably interpreted, as I'll get into a little bit on the next slide, but basically that you have some other source of C2 which is turning on as the comet moves closer and closer to the sun. Okay, so a little bit more on kind of the origin of these molecules that we actually observe with ARSIS. So these molecules are what we call fragment or daughter species. So these are not molecules that are inherently present in the comet itself. They are produced via photochemistry in the coma, usually the photodissociation of some more complex molecule. So these are the species that we observe in the optical. However, kind of more from a scientific standpoint and trying to tie back to the protosolar disk phase, we're more interested in what we call the parent species. So these are the ices that sublimate directly from the nucleus. So these are things like water, carbon dioxide, hydrogen cyanide, ethane, ammonia, etc. That we're interested in. However, observations, since these species can only really be observed at IR and submillimeter wavelengths, there's relatively few of these observations compared to the fragment and daughter species, which are observable in the optical, which is a lot more accessible, just both historically and also with current instrumentation. So what we really like to do is understand that photochemistry that links these fragment and these parent species in order to better interpret these optical abundances or optical observations in terms of the composition of the comets. So we've been, so basically that's what I'm saying here, just comparing the daughter species. So what we want to do is compare these daughter species abundances to candidate parent molecules to better understand this coma photochemistry that's occurring. And what we've been doing with APO is been having contemporaneous observations with APO ARSIS, but also making them contemporaneous with infrared observations at facilities such as Keck Near-Spec or NASA IRTF. So in the early days, it was Seashell. More recently, we've had this new instrument called iShell, which provide infrared spectra. And what we can do is basically create diagrams like this, where we can compare the daughter species, which are in blue here, to the candidate parent species, which are in red. So you can see here for this comet 103P Hartley 2 that there's enough hydrogen cyanide and ammonia to account for the NH2 and CN we observe, but not enough acetylene or methane to account for the CH and C2. And this has often been interpreted as that there's some other source of the C2 and CH that's probably not a classical simple molecule, but something more like a carbonaceous rich dust grain or something that's sublimating and releasing these fragments into the coma. All right, so a very specific example of this is the forbidden oxygen lines, which you really can only access at high spectral resolution because there's a strong telluric counterpart to all these lines that you need to be able to resolve it from. So in comets, this O1 emission results from photodissociation of water and carbon dioxide molecules. And this is important because carbon dioxide is a very abundant molecule in comets. It's often the second most abundant molecule, second only to water. But we can't really observe it directly because of severe telluric absorption from the Earth's atmosphere. So if we look at the flux ratio of certain forbidden oxygen lines that we observe, to measure what we call the oxygen line ratio, this ratio can be indicative of the parent species, whether it's water or carbon dioxide, where the oxygen is coming from. And if we understand this photochemistry completely, we can actually use this as a quantitative proxy for CO2 in comets, which would be very powerful because this would be a ground-based way to measure carbon dioxide abundances. However, the problem is we really don't understand this photochemistry well enough to use it reliably. So what we have been doing, so a lot with APO, but also a little bit with McDonald, we've been obtaining oxygen line measurements for comets that also have CO2 measurements available from spaceborne facilities. So mostly Spitzer Space Telescope and the NEOWISE mission, but also, archival from, let's say, the Akari satellite, for instance, as well. And we've been trying to calibrate our understanding that we can actually take, an inferred CO2 abundance from our oxygen line ratio and actually have it correctly reproduce directly measured CO2 abundances from these facilities. And so this is kind of preliminary results from a small set of our sample. We have almost about 30 comets in our sample. And the blue line here is just kind of a guide to show that, kind of where they are equal. And you can see we're doing a pretty good job, but there's still a lot more work that we need to do. All right, so I want to finish up here in the couple of minutes I have left with a couple of very interesting individual comets so that we've been studying. So one is a comet called C2016 R2 Pan-STARRS. And this comet kind of reminds me of a couple quotes that are around. That one is ascribed to comet discoverer David Levy. He says comets are like cats. They have tails and they do precisely what they want, just meaning that they're very unpredictable and they never seem to conform to your expectations. And the other one that's ascribed to Isaac Asimov is the most exciting phrase to hear in science. The one that heralds new discoveries is not eureka, but that's funny. And this comet really fits that bill. So, because when we took spectra of it, we didn't really see any of those usual features that we see, the C2 and that CN that usually dominates the optical spectrum of comets. Instead, we saw all of this strong CO plus and N2 plus, first with McDonald and then also in observations with ARSIS as well. And this is actually the most definitive detection ever of N2 plus in a comet. So this was very surprising and really emphasized this comet as needing follow-up from other facilities. So we were able to obtain other observations on facilities such as Spitzer and NASA IRTF iShell to fully characterize the composition. And we found that it's really completely different than any comet that we've observed. So on the left here, this is kind of what your average comet looks like. It has mostly water, carbon dioxide, CO, and then a smattering of other stuff. Whereas this comet is actually mostly CO with a large molecular nitrogen abundance and water really relegated to the status of a trace volatile. So this is really peculiar. None of the models really predict that comets should form like this. There's a lot of theories about what this could mean, including that maybe it's a fragment of like a Pluto-like object that broke apart. Maybe some weird chemistry that we don't fully understand in the disk at the time that it formed. Or it could even be an interstellar object, who knows, that we captured. And lastly here, speaking of interstellar objects, so probably the most high profile result that we've had is that we were able to detect with ARSIS atomic oxygen in 2I Borisov, which is the first unambiguously interstellar object that interstellar comet that we observed. And we were able to use this as a proxy for water, and this provided the first measure of water production in this interstellar, in an interstellar object. And this got a lot of nice press release, press attention. It was kind of a big news. And since I'm kind of running into my time, I will just go to this slide saying that comets are awesome. And hopefully you learned a little bit about comets in this very brief overview of our program, and I will take questions. Thank you.
All right, thank you. Let me see if I can quickly scan. Yes, Hannah, do you want to go ahead and ask a question?
Oh, I was just clapping.
Oh, you're clapping. Okay, sorry. Oh, that's a clap too. Okay.
Oh, but I did, and now I have one.
Okay, Nancy, go ahead.
So Adam, I can't remember. I feel like I should know the answer to this, but it's been a while since we've worked together, so you can humor me. Do you have the ability to make rotationally resolved measurements of these things on a given night or given observing run so that you could start to think about different sources on the surface for different types of volatiles?
Yeah, we definitely can. I mean, that kind of varies from comet to comet, and how long it's available in a given night and what the rotation period of that comet is. But we have done that in some cases. Probably the most high-profile one we did was for 103P Hartley 2, where we had back-to-back nights, when it was available for pretty much the full night. So there we had a long baseline, and we were actually able to see some kind of variation in the production rate over time, which is most likely ascribed to the rotation of the nucleus.
Thanks.
All right, and Kevin, do you want to ask your question really quickly?
So for the comet with the strange composition, is there anything else unique or different about it? Like, is its inclination significantly different? Is its eccentricity significantly different for some major axes? Like, what else is odd, or is there anything else odd about that object?
No, yeah, that's one of the weird things, right? Yeah, because that's the first thing you look at. It's like, oh, is the orbit, something like Borisov, where it's clearly hyperbolic and it's an interstellar, has an interstellar origin. But this is, it's not even particularly what we'd call dynamically new. It's probably not even its first passage to the inner solar system. Its orbit is about 20,000 years or so. So it's been through the planetary region at least several times before, even. So yeah, so there's nothing weird about its dynamics. Or really, it was just kind of, initial, really the spectrum, the composition is kind of the only thing that's really peculiar about it.
And then as someone who's not a comet person, how much of an outlier is it? Is this a 1 in 100 event, a 1 in 1,000 event, a 1 in 10,000 event?
Yeah, it's kind of hard to put. I mean, so certainly, if you kind of compare for our comets, like at least the optical, we have over 200 comets in our optical taxonomy, and none look like this. The only comet that looks, based on kind of optical spectra that looks remotely like this is, I'm blanking on the name, but it was a comet like in the 60s, before we really had any of this modern, really before the age of CCD detector. Like, this is just somebody took a spectrum on a photographic plate and it maybe showed like CO+ and N2+ in it. But that was 50, 60 years ago. So this really could be a once in a generation kind of object. We don't have so it's certainly an extreme outlier, and also by orders of magnitude, not like by a factor of a few, by orders of magnitude compared to other comets. So that's really the next step, is to kind of continue our surveys and see if we can find another one, so we can better understand how common these objects are, because I'm sure that'll have tremendous implications for the origin of these types of objects and what they're telling us about the early solar system.
Okay, great. Thank you, Adam. Let's move on to our next speaker. Our next